So to deal with this kind of scenarios, in the Bracha broadcast there is actually an additional phase which is called the ready phase. So what happens that the process receiving two f+1 echoes of message M will not deliver M straight away, but will instead broadcast another message, a new type of message, which is the ready message, and the ready message will carry M as its payload. Then a process receiving two f+1 copies of readies for message M can actually deliver M. And of course, if it was not delivered before, so we can avoid duplicate deliveries. So that's not all. So there is an additional step here, which is called amplification step. And amplification step is executed at any point of the algorithm at which a process receives f+1 ready messages for some message M. Okay, so once that happens, a process will broadcast ready message as well. Okay, so notice there are two cases when a ready message can be broadcast. So the first case is when we are receiving two f+1 echoes of message M. So we broadcast ready for message M. And another case, if we received f+1 copies of the ready message for M, then we also broadcast the ready message for M. So notice that it's actually okay to do this, because the fact that we are seeing f+1 copies of the ready message means that at least one of them was sent by a correct process, and therefore message ready for message M was indeed broadcast, and so this is okay to rebroadcast it again. Okay, so for that reason, amplification step would actually not violate any kind of correctness guarantees. And as we will see, the proof of totality relies on the existence of this amplification step. So this completes our presentation of the Bracha broadcast algorithm for Byzantine reliable broadcast. And now let's see why it is correct. So no duplication is of course trivial, because a process only delivers a message if it has not delivered the same message before. So now let's see why integrity and consistency also hold. So let's assume that a correct process P delivers a message M. So that means that P has necessarily received at least two f+1 messages ready with the message M as its payload. So that means that these ready messages were sent by at least f+1 correct processes. And therefore there is at least one correct process, say Q, that actually broadcast this ready M message. So, and when that could happen? So that could happen either following the delivery of two f+1 echoes of M, or following receiving f+1 ready messages for M. So in the first case, so when Q received two f+1 echoes of M, we already know that delivering such a message M won't violate integrity and consistency. And we have argued that when we considered the analysis of the echo phase. Now in the second case, so the second case can actually stem from the existence of the amplification step that we discussed. So in this case, we know that there is at least one correct process that broadcasts the ready message. And so we can repeat this argument and basically follow the chain of ready broadcasts down to the point at which some process actually broadcasts a ready message following receiving two f+1 echoes of this message. And once we arrive to this process, we can again apply the argument that we discussed in the echo phase analysis and conclude that integrity and consistency are both satisfied. So now let's see why validity holds. So to prove validity, we actually have to assume that the sender is correct and sends a message M. So then this message M will, of course, reach two f+1 correct processes because the sender is behaving correctly and will follow the protocol, and therefore it will complete the initial broadcast phase at all processes. So once this message M reaches two f+1 correct processes, they will broadcast echo of this message M. So all correct processes broadcast the echo of message M, and that means that all correct processes will receive at least two f+1 echoes of message M. And this is simply because we have two f+1 correct processes and all of them will broadcast the echo message. So once all these correct processes will receive two f+1 copies of M's echo, each of them will also broadcast the ready message for the message M, which means that every correct process will eventually receive two f+1 copies of the ready message with the payload M. And again, this is simply because we have at least two f+1 correct processes and all of them will broadcast the ready message. And so once we see two f+1 messages ready M, then we can, of course, deliver M according to the protocol, and that satisfies validity. So this may sound a bit complicated, so let's look at the example to see what actually happens here. So in this example, again, we have four processes and we have a sender P1 and it is actually correct. Okay. So there is also a Byzantine process, but this process is not the sender. This is this process before here. So the sender then initiates the initial broadcast phase and it will distribute, since it is correct, it will send the same message M to every other process, including a Byzantine one. So after receiving this initial broadcast, every correct process, of course, will follow the protocol and will rebroadcast this message. It will echo message M. Okay, so that will happen for process P1. So it sends echo to itself, process P2, process P3, and process P4. And process P2 sends echo to itself, to P1, P3, and P4. And the process P3 will send echo to itself, P2, P1, and P4. And say P4 is Byzantine and it will not cooperate, it will not follow its protocol, therefore it will not echo this message. So all these blue messages here are echoes of message M. Okay, so now we can just do the counting and see that message M, the echo of message M now received exactly 3 times at every process. So 3 is of course equal to 2f plus 1 in this case, and it means that every process is guaranteed to initiate the ready phase and broadcast the ready message. So this is indeed what happens. So every process will send a ready message. So they may do this at different point in time. So at any point after they received these 3 echoes, they can go ahead and start broadcasting the ready message. So process P1 can do it here. And process P2 can do this here. And process P3 may do this here. And again, let's say process P4 does not cooperate and is doing nothing, but actually whatever process P4 can do here to try and harm the protocol, that won't help. So just for the sake of the example, we can say that, for example, process P4 here is trying to disrupt the protocol and say it will, at this point, it will send a ready message for something else here. So all the yellow messages are ready messages for M, and then this purple message here is actually a ready message for something else, message M prime. Okay, so it may try, of course, to do this. But that won't help, because all processes here, as you can see, can receive at most one bogus copy of this message M prime. They won't receive, they would never receive 3 copies of that message, and therefore they won't act on this ready message of P4. Okay. On the other hand, they do receive 3 copies of the ready message for M, and so they will act on it. So every process will receive these 3 copies, as you can see in this example here, and therefore they will deliver message M at some point. Okay, so they may deliver it here, 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 and here. So that's deliver M, and so we have validity. So now we are left to prove property 5 of Byzantine reliable broadcast, which is totality. So to prove totality, we have to argue that if some correct process, say P, delivers a message M, then eventually all other correct processes will also deliver M. So let's start from this. So let's assume that the correct process P delivers a message M. So from that, according to the protocol, we can conclude that P has necessarily received at least 2 F+1 ready messages with the payload M. And from this, given that we have at most F Byzantine processes in the system, we can conclude that there are at least F+1 correct processes that actually broadcast these ready messages that have been received by P. So since these F+1 processes that broadcast ready M are correct, their messages, so these ready M messages, will eventually reach all other correct processes in the system, and there are 2f+1 of those. Okay, so at this point we have that all correct processes, all 2f+1 correct processes in the system received, each of them received f+1 ready M messages. So at this point, what happens is that amplification step will fire up, and it will cause each one of these 2f+1 correct processes to rebroadcast this ready message for M. Okay, so once they have done this, we now have 2f+1 messages sent by every correct process to all other correct processes. And since we have 2f+1 correct processes in the system, that guarantees that 2f+1 ready messages will be received by all correct processes. And this is the condition for triggering the delivery of message M, and that means that all correct processes will deliver M, and therefore we have totality. So this completes the correctness proof of the Bracha broadcast protocol.